Nuke incoming!
Why we care about nuclear physics. Have you ever asked yourself these questions? What is nuclear matter? What are its properties? What holds the nucleus together? Why doesn't the repulsive electrostatic force blow it apart? What is the connection between the nucleus and radioactivity? If so, you're a nerd, but also probably really smart trying to make the world a better place. So go you. In this lesson, we will attempt to teach you some of this because that would be good to do. Nucleons. The nucleus is a tiny speck in the center of a much larger atom. The nucleus, however, is 99.9% of the atom's mass. The nucleus is composed of two types of particles, protons and neutrons. Together, they make nucleons. The importance of nucleons? I put it in bold. The textbook put it in bold. Now your mind should put it in bold. Jason, give the camera a thumbs up.
Atomic number. The atomic number is the number of protons that a certain atom has. Each element is defined by the atomic number. Boom. Carbon 12. The atomic number is 6, which is exactly the same number of protons it has. Boom. Carbon 14. Its atomic number is 6, the same number of protons it has.
Alright guys, this should be a great review from chemistry in sophomore year, but that's okay. So I will start out with mass number. The mass number, as all of you should know, is the total number of nucleons in the nucleus, where nucleons refer to protons and neutrons. Mass number, mathematically, is often shown as A equals Z plus N, where Z is the number of protons and N is the number of neutrons. And of course, again, as you remember, the protons are the positive charged ones and the neutrons are neutrally charged. You can always remember by looking at the happy and the neutral little circles here.
Isotopes and isobars. I'm losing the will to live. Sometimes atoms of the same element have different amounts of neutrons bonded together. These are called isotopes. Sometimes it is known as having the same Z value but different A value. Boom. So these are isotopes of a hydrogen atom. Just in case you forgot, that's A. And that's Z.
Next, we will talk about isobars, which are different elements with the same atomic mass, as pictured down here. The Martok isobar rule states that if two elements adjacent to each other on the periodic table are isobars, at least one of them will be radioactive. For instance, carbon 14, nitrogen 14, and oxygen 14 are all next to each other on the table and are isobars where A equals 14. But only nitrogen 14 is stable. The other two are radioactive. The only exceptions to this rule are that of antimony 123 and tellurium 123 and tantalum 180 and hafnium 180.
There are more than 3,000 isotopes known. Most of these are since the nucleus is not stable. After a short period of time, these unstable nuclei will fragment or emit a subatomic particle in an attempt to stabilize. Most isotopes are created in laboratories and have a short existence. Sorry, that stuff's not for you guys, so let me pause that and I'll come back to that later. Scoop-dee-whoop-dee. Okay, so you know how we were talking earlier about radioactivity and how there are less than 10% of stable nuclei, which means not radioactive. There's like a way to kind of like look at that and kind of glean some information and know which ones are stable and not stable, and so we're gonna take a look at that. So this graph really represents a lot of what's going on, and but you're like, wow, this is really overwhelming. Like, look, there's words and stuff like everywhere, and you're like, wow. Let's take it back for a second. So just kind of get a good mental image of what's happening. So you're looking at your axes, other axes, and you're looking at those two lines and a bunch of dots. Keep those in mind. We're going to take a look at the bottom now. Here's some observations you can see. Stable nuclei clusters very close to the curve, called the line of stability. And look at that. Line of stability. They even got a label for you. That's amazing. Go textbook. You're really good. Okay. Right down here. There are no stable nuclei with Z greater than 83. You're like, whoa, proton number. 83 is probably right around here. Whoa. And then look at that. No more nuclei. So you're like, wow, textbook spot on. Once again, great job. And I'm just gonna leave these here for a second, so that way you guys can get an image and then like understand what's going on, and then I'll pan it back to that, so that way you can look at it. Just kind of reading along. Bum, bum, bum. You can pause the video now. That'd be cool. And you're like, whoa, all this stuff makes sense now. Thanks, Will. You're amazing. So that's some nuclear stability. That's the very basics of it, and physics C.
Hi, welcome to Chili's.
We are going to review another topic from chemistry, natural abundance. Natural abundance is the abundance of naturally occurring isotopes of an element. Some only have one naturally occurring form, such as iodine, while others have several forms. With iodine only having one natural form, the natural abundance of iodine-127 is 100%. However, with isotopes such as uranium-238, 235, and 234, it is not all the same. Uranium-238 makes up 99% of the world's uranium, while 235 and 34 make up the rest. Now, natural abundances can change over time because of differing half-lives. For example, uranium-235 used to make up 3.1% of the uranium, which would have allowed a natural nuclear fission reactor to form. But that can't happen anymore because now it only makes up 0.7% of the uranium.
Atomic mass units. Atomic masses are measured in terms of atomic mass units, U. This measurement is defined so that carbon-12 is exactly 12 atomic mass units. Alternatively, you can write 1U as 931.49 MeV over C squared, which is cool if you know what that means. Also, check out this cool table. It's got the measurements for other common things. Look at that. That's cool stuff. You should read that.
Nuclear size and density. Big R equals little r times A raised to the 1/3. Big R is the radius of the nucleus with mass number A, and little r is 1.2 femtometer, which is 1 times 10 raised to the negative 15. On the graph below that, we see R per femtometer over A. The curve is basically A raised to the 1/3.
You might not have the test printed out. Which would be
That is line. But that line is the slope of 4 pi r squared divided by 3 femtometers over A. For nuclear density, density equals mass number A times the atomic mass divided by 4 pi r cubed divided by 3,
That's not good.
which equals 2.3 times 10 to the 17th kilograms per meter cubed. In the equation, big R is replaced by the equation at the top left, and A gets cancelled out. This means the nuclear density of all atoms is relatively 2.3 times 10 to the 17th kilograms per meter cubed.
Yeah.
I sent it to someone a long time ago.
Good job, Jason.
The energy increases as atomic mass increases because there are more nuclear bonds to break. And this illustration here shows binding energy being separated, or being used to separate the nucleus.
Okay, actually go.
Alright, bring it back in, pimps and players. 4 important properties of the strong force. 1. It is an attractive force between any 2 nucleons. 2. It does not act on electrons. 3.